Hi, Assalamualaikum warahmatullahi wabarakatuh. So in this video, we are going to start off with the properties of the integral. So the first property is saying that if c is a constant, and when you want to find the definite integral of a constant, it will be just c multiplying with b minus a. So b is the upper limit and a is the lower limit. Now, when you have two functions add up together, and if you want to find the integral of these functions, these added functions, what you can do is you can separate them and evaluate them separately, and based on that, you can get the sum of it. Okay, so that's the second property of the integral. Now, the third one is if you have a function fx and you have a constant, so c here is a constant that is multiplied to that function. In order to integrate this function, you can take out the constant. So c can be taken outside, so you can brought it forward, you can put it aside first, and then you evaluate this function. Okay. The fourth one is similar to the idea of the second one. So the fourth one here is similar to the idea of second property, except that we have a subtraction process here. Now for the fifth one, if you have a function, for example, fx is a function evaluated from a to c, and then you add up with this function, the same function, you want to find the integral of it from c to b. Now this process can be simplified by integrating this function from a to b. So let me just give you an idea based on a simple sketch. So let's say this is a function. The function is looking like this, and if and this is function fx, and for example, the interest is to evaluate from a to c. So this is to evaluate this function from a to c. So let's say this is point a and this is point c. So the process of finding the integral of fx from c to a is the process of finding the area under the curve. So that is from a to c. Now, if you look at the second part here, you will evaluate this function, the same function, which is fx here, but this time is from c to b. So you continue from c to b. So let's say this is c and going to b. So the process of finding the integral here is the process of finding the area under the curve. Now, these two processes here can be combined and can be written simply as this. From b to a, so from b to a, b is the upper limit, a is the lower limit. So you write down b to a, and fx is the same function, so fx dx. So the process represented here is the process of finding the area under the curve from point a until b. So that's the idea of the fifth property of the integral. Next, let's look at the sixth property of the integral. Now, if fx is greater or equal than 0 for x between a and b, then this integral here will always be greater than or equal to 0. Okay, so what it means is that if you have a function, so if you have a function fx, so this is fx, and fx is always greater than or equal to 0. Now, how do you know that it is always greater than or equal to 0? Because 0 is at this line. So this is my fx. So this is my fx. This is my fx. Okay, so this is fx. So this is also my fx. So clearly, this fx here is always greater than or equal to 0. And because of that, if you evaluate its integral, the integral is going to be positive, greater than or equal to 0. So that basically means that if I have a function fx that is less than or equal to 0. So this is 0.0. So this is my fx. So this is fx at this point. So this is also fx that is less than or equal to 0. This is also fx. So if you evaluate the integral from this interval to this interval, the answer here is going to be less than 0, okay, or equal to 0. Okay, right. Now for the last property mentioned here, if fx is greater than or equal to gx for x between a and b, then this integral will always be greater than this integral. Okay, so how do we visualize that? Okay, let me just sketch something simple for you to see. Okay, so basically what we have is we have this function here. Let's say this is the function of fx from x from a to b. Okay, so next is we are going to have gx. Fx is always greater than or equal to gx, so gx may be this one, maybe just a straight line, so gx. So clearly for x between a and b, so in this interval between a and b, you can see that fx is always higher than gx. So you can see that this point is always higher than this point is always higher than this point is always higher than this point. So fx is greater than gx, and because of that, if you want to find the integral, of fx dx from a to b, the result here will always be greater than or equal to the integral of gx dx from b to a, from a to b. Okay, so the result here will always be greater than or equal. Now why is it so? Because you can see that when you talk about the integral, when you talk about finding the integral of fx, you're talking about finding the area from this onwards. So this is the area of fx. It's bigger, clearly. So the area here from this curve until this. Okay, and if you talk about the area of fx, the area of gx, the area of gx will be evaluated from this line until this horizontal axis here. So clearly, based on that, the area for fx is bigger than the area for gx. Okay, now let's talk about the first fundamental theorem. If f is continuous on this interval, f is continuous on a and b, then the function f defined by this, so this is the function big F. So big F is defined by this. So big F can be found by integrating f. F is a function here, f d dt, with respect from a to x. Okay, from lower limit a to upper limit x, where x is between a and b. So according to this theorem, the big F here, the fx here is also continuous on the same interval, and it will be differentiable on a and b, where the derivative of big fx here will be equal to fx. Okay, what is going on actually? Okay, first of all, there are some mistakes on this slide, so please correct them. This is actually big F. Okay, so this is actually big F. Now notice that the function big F here depends on x. So this function here depends on x, and x appears as the upper limit. Okay, in other words, the big F here is called the antiderivative of F. So what is antiderivative? Antiderivative is when you have the situation that big f prime x is equal to fx. So we say that big F is antiderivative of f. I'll give you an example here. So let's say fx is x squared. So this is a small f. So antiderivative is something that when you differentiate it, you will get back fx. Okay, so if fx is x squared, okay, so if fx is x squared, can you come up with a function which is big F such that when you differentiate this function, you will get this back? So for example, the function could have been x cubed over 3, and when you have this function, okay, so when you have this function, if you differentiate this, so if you differentiate this one time, you will get that the answer is 1 over 3. 1 over 3 here is a constant. You differentiate x cubed, you will get 3x squared. So 3 can be cancelled. So you get f prime x is equal to x squared, which is just this one. So that's the idea of antiderivative. Antiderivative is a function where if you differentiate the function, you will get back the small f function. And you can have many options for an antiderivative function. For example, for this question here, the first antiderivative could be this function. This could be an antiderivative. But if I have another function, let's say gx, so gx here is given as 1 over 3 x cubed plus 10. So this is gx. And you can see that if I differentiate this function, I will also get x squared, which is this one. Okay, you can go on try differentiate this. If you differentiate this, you will get 1 over 3 is a constant. And then x cubed here, if you differentiate that, you will get 3x squared. Plus, if you differentiate 10, you will get 0. So then it will be reduced to just x squared, which is similar to fx. So there are many options of antiderivative. So this is the first option. This is antiderivative. This is also antiderivative because when you differentiate it, you get back fx. So in general, I can say that the antiderivative can be anything in this form, which is 1 over 3 x cubed plus c. C is a constant. It can be anything. It can be 10, it can be 12, it can be 100, it can be 1000, it doesn't matter. So you have many options for that, for the antiderivative of f, okay? Okay, so now I'm going to illustrate a simple example. So it is asking you to find, in this example, it is asking you to find the derivative of this function, where this function is defined as this one. So what it is saying that basically it wants you to find what is g prime x, derivative of gx. So what is g prime x? Now, when you look at this function, when you look at this gx here, so gx is equal to x0, 1, the square root of 1 plus t squared dt. So if you look at this definition of gx, you will see that it resembles the idea of fx, x0, ft dt. So this is the idea given in the fundamental theorem just now. So fundamental theorem given here. So you can see that this one. Okay, so this is the idea here. So 0 here is your A, X is the same thing, FT is this one. Sorry, this is A. So FT is this one. So based on the idea of fundamental theorem, I can find that the fundamental theorem states that therefore f prime x is equal to fx. So this is the idea of fundamental theorem. Now I want to find what is g prime x. What is g prime x? So therefore I know that according to the fundamental theorem here, g prime x will be equal to ft. And you will replace t later on with x. So g prime x will equal to this one, and I'm going to replace t with x. Okay, so let me just put it straight away as x. Okay, so g prime x will be equal to this one, which is ft, and then you're going to substitute x into that. So g prime x is just 1 plus x squared. So that's the answer to this example. Just a simple example to illustrate the meaning or the idea of this theorem given here. Alright, okay, that's all from me. Thank you very much for watching, and I'll see you in the next video.